there are tree traversals. Generally you have a tree, so you have, this is called left node and this is called right node. So in a binary tree you have left node and right node to the parent node. So how do you traverse the tree? So that's what we talk about, tree traversals. So there are four ways. One is in order, or first one is so there are four ways to traverse the tree. So first one is pre-order. So pre-order means, so first you will have a root, then you will move on to left, then you will move on to right. This we call it as pre-order. So let's say this is left node, this is right node. So this happens recursively. So let's say this is your tree. So if I want to go with pre-order, so this is how it looks like. Let's take this is your tree. So if I want to talk about pre-order, so this is how it looks like. So first you will visit this one. Okay, so let's take this is one. First you will visit this one, because first you traverse from root, right? So I went to root, so I got one. Then you should go on to left. Okay, so once you go on to left you get two. Then, so generally what how it should work is, when you are working on pre-order, root left right, so it works recursively. So at each node you should apply. So let's say I am at root, so root 1, then I need to take the left. So once I take left I get value 2. Now if you closely see, this can be act as a subtree. Okay, this can act as a subtree. So if you closely see, this is my subtree. So when you get a subtree, so it means again, uh, so simple. So you will go on to root, then move on to left, then move on to right. So whenever you are trying to traversing right, first you should complete the current directory, current root path, then you move on to other path. So first of all I went on to root, so which is 1, then I try to went into left. So when I went to left I got 2. Now I cannot directly get into right because I need to solve this subtree. So I need to solve this subtree. So again same concept. So let's say you went into left, then, so yeah, so this is root, and from root you gets into left, so left is 2. So but when you went into left, think this as a subtree. So this is how it got, right? So think this as a subtree. So you got a subtree. So when I went to left I got a subtree. Now it's time for me to solve this subtree. So if I want to solve this subtree, so this is my root now, so I take that root. So once I take that root, and again I went into left. So when I went into left, so this is my subtree. So this is my subtree. So I got 4. 4 doesn't have left and right. So I'll just blindly take that root. So that is going to be 4. And 4 doesn't have left, doesn't have right. It means from this root you derive left. So this is done. Then it's time for us to derive right. So the right is 5. So just take that 5. And if the 5 has any subtrees, then you could have look into them. So the right doesn't have any subtrees, so that you just took that. If you closely see, from 1 when I take left, this is a subtree I got, and I just derived that subtree through pre-order traversal. Then I am done with left part. Then it's time for me to look into right part. So the right part will have 3, so that I just need to return 3. Is this clear, buddy? Or did I make it complex? Okay. So let's say you have a tree something like this. Let's say you have tree 1, 2, 3, 4, 5, and 6. If I want to go with in order, sorry, this is pre-order, right? So if I want to solve pre-order, so first of all I should go with the left. First I should start with the root. So this is my root. Okay, so I start with root 1. Now closely see this part, then I should move on to left. When I move on to left, if you closely see, this is my subtree again. So this is my subtree. So I need to apply the same concept. So if I want to go with pre-order concept, so this is what it is, right? So pre-order, so it should be root, then explore complete left part, then after exploring complete left part, then explore the right part. Now what I'm doing, so I'm starting from root. Okay, so I got 1. Then I need to explore the left part. So when I explore the left part, I could see this is a subtree. Now I need to start, so when it is a subtree, again I need to follow the same process. So this is my root now. So my root is 2 now. So let's move on. So I'll take that 2. Okay, perfect. So once I take the 2, then I need to explore the left part, because again same concept, right? So I need to explore the left part for this subtree, but there is no left, so that I can directly move on to the right part. So when I move on to the right part, again I got the subtree. So this is 4, 5 is the subtree. So again I need to apply the same pre-order concept. So when you consider this as a subtree, so I can say that this is the root. So the root is 4. Okay, fine. I take 4. So it means you are done with this 4. Now it's time for us to explore left and right. But if I am exploring left, I could find a tree. So that I just take that tree, which has only one value. So there are no sub-chains. So I can blindly take that 5. I can blindly take that 5. Then if I go left, it is null. If I go right, it is also null. So that we are done with root left. Then yeah, as it doesn't have left, so I went to right, and this doesn't have right, so I went to left, and when I go to right, there is no right, so that I just done with it. Now if you closely see, from this root I started from this root, so I explored the complete left part. Then it's time for me to explore the right part. So now to explore the right part, so on the right part I could see one subtree which is starting from node 3. So just take that 3. Perfect. So once you are done with 3, now it's time for you to explore left. There is no left, so that it's time you can blindly move on to the right. On the right you have value 6. Just take that 6. It doesn't have left and right. So this is what the pre-order traversal looks like. Is this clear? Is this clear, buddy?
Yes.
Maithili, are you clear? Yeah. Now, how do you write a logic for this? How do you like it? How do you write a logic for this, please?
Start from root and then move left and right.
Yeah.
Again, apply the
Uh,
same logic on the consecutive root, whatever we get from left.
yeah. So let me take the order. So this is the order we followed, right? Okay. So first we started from.
Will we use double linked list here?
Okay, to construct this one, right? So it's not like, okay, we will get into that. Yeah, we'll get into that. Just a minute. So I will just maintain the order. So this is first element, and this is second element, and this is our third element, and this is our fourth, and this is our fifth, and this is our sixth, right? So that's how you traverse. So that's how you get the data. Yeah, so to construct a binary tree, right? If somebody says to construct a binary tree, how does it look like? So this is my tree node, and it has value, and it has left, and it has right, right? So that's how it is. So first you have a root, then root dot left. Again you try to construct. Yeah, so this is how it should be, construction of binary tree. I think we don't look for the constructor of binary tree, but you can take a look into it. So you just need a object tree, value left and right, and you keep on constructing it. Okay. Now, if I want to solve pre-order, it means you will be already given a binary tree and with the root node. Okay. So you will be given a binary tree with the root node. So this root node, and which is being constructed. So it has a tree object. So you have a value, which means node value, and left and right. So this left is pointing to again another tree object, and right is also pointing to another tree object. Now, if you want to, you will be given a tree root node, and you want to construct a pre-order. How do you do that? You should return a list of integers. How do you do that?
Can you come again? The question, please.
This is your binary tree. Okay, this is your binary tree. They already given a binary tree to you, and they just given a root reference. Okay, so root has value 1, it has left, and it has right. Right has value 2, right has doesn't have left, but it has a right 4. You understand? So it's a binary tree, right?
So now we can begin with a base case, like if the root is null, then
Yeah,
return
we
from
will
there.
we will go to that. I think they have a problem with how the problem statement could be. Let me explain. So you will be having a tree node, and it is having value. It is having value left and right. Okay. So the value is talking about value of the node, and left is pointing to left child, right is pointing to right child. So this is how it should be. And what the problem statement says, you will be given a root. Okay, they already construct a binary tree and they will given a root. We just need to return the pre-order for it. For example, if you take this is the root, this is the tree they given. The pre-order should be so yeah, this is the root they given. The pre-order will be root. There is no left, so you can go on to right. So which is 2, and there is a left 3. So pre-order will be 1, 2, 3. So when it comes to this, the pre-order will be 1, 2, 4, 5, 6, 7, and 3, 8, 9. So that's how it should be. Clear, na? Problem statement clear, na? Kalyan? Yeah, so how do you want to solve it? How do you want to solve it? Okay, so let's take this input. Okay, so this is fine. So this is good input so that you can explore all possibilities. Yeah, Ajay, you can continue now. You can proceed now. What are the ways to solve it?
Base case. So basically, I was thinking to do a depth first search here.
Yeah,
So define another method for DFS
that's it. That's
and
it,
pass.
right? Right. Okay. So DFS will take what?
It will take the root node,
Root node, then list,
and
right?
here we're returning a list of integer, right? So for that
Yeah.
we need to
List.
define a
Okay.
list of
List
list
of
for the result.
Perfect. So what? How it works then? Now?
Now we will check if the root is null, just do nothing.
Mm.
Otherwise, we will add the root dot value to the list,
Mm.
then go left, then go right.
That's it. So that's how the DFS logic, right? So if you say DFS, so let's say you have root and you have list. Okay. So how? What is the first? What you do? First, you always generally you see in a pre-order, right? First you visit a root. Okay. So the root is 1. So 1 is being added to the list. Okay. Then what is your job? You go on to the left. Okay. It means you go on to this. So you just need to call DFS of 2. It means you call this one, and once you are done with this, then you will call DFS of 3, right? So DFS of left and DFS of 3. So what will happen? First you call DFS of 2, right? So first it will went to DFS of 2. So first again it will add 2. Okay, so this is how it should be now. So if I directly write the diagram, so first you will make a DFS of 1. What it does, then DFS of 1 will call DFS of 2 and DFS of 3. Right, first it will call this one. First it will call DFS of 2. Then DFS of 2 will call DFS of null. Right, so DFS of null because it has left as null, so that it went on to right. Then it will call DFS of 4. DFS of 4 will call DFS of 5. And also it's right also DFS of null. Perfect. So similarly DFS of 3 also will call DFS of null because it doesn't have left, and DFS of 6. Right. So the order how it works. So first it will start from here. First you call DFS of 1, so that 1 will be taken. 1 will be taken. Then you went on to the left. Okay, left is DFS of 2. So 2 will be taken again. Now again you call left. So DFS of null. So null is means this is the base case. When it is null, you don't do any operation, just return. Right? You don't do any operation, just return. Now once you are done with DFS of left, now you went on to DFS of right. So right is 4, right? So you will pass 4. So 4 means first you will take 4. Already you taken 1, 2, now it is 4. Now from 4 you will go on to the left. So DFS of 5, so which is going to be, so it means whenever you call a recursive call, you will just take that value, and when you just do the same operation, right? Simply DFS of root dot left, and DFS of root dot right. So that's it. So this is your logic, and you will just add list dot add of root dot value. So that's it. So if the root is null, you don't do this operation. So if the root is null, simply you will just ignore, right? Is this clear, buddy? Or I thought you already know this, so I went little quick. But do you need clear explanation, or is this clear? Okay, let me explain. What is our core logic? So when it comes to pre-order, right? When it comes to pre-order, so what is our core logic? First, you need to explore root, then left, then right, right? So this is our core logic. So what you do? So first you will call DFS of root. In this case, root is 1. So whenever you are exploring the root, you take that value. So it means you take the value 1 and add it to the result. Now next is lot, we need to explore left. Okay, so let's explore left. Left for root, this is root, right? Root dot left is 2, so that you will explore DFS of 2. Again you will take that root value, done. Now again you try to explore left, so it is DFS of left is null, because for this root 2 there is no left, left is null, so that when it is null you will just return, so this will be terminated. Now you want to write. Now right is going to be DFS of 4, because root left right, right? So DFS of 4, so 4 you current root value you consider, then move on to the left. So again DFS of 5, so current root value 5, so because 4 left is 5, so 5 you will be taken, then you will move on to the right, so which is going to be DFS of null, because there is no right pointer, so null. So when it is null you will just terminate it. And even when you go on to fight, it will move on to left and right, but both will have null, so that there won't be any operation here. But when it comes to here, null directly, so you will be done. So if you closely see what I did, so I started from root 1, then explored left. From this left, when I go left, I got null, so that I went on to right, and from this right I went on to left, and from this left I went on to left and right. So these are null values, so that it won't do any operation. And when I go on to right, again it is null, so it won't do any operation. It means from root 1 I explored complete left path. Now it's time for me to explore right path. So if I want to go right, so it is going to be DFS of 3, right? So you will take that 3, then again left. So DFS of left is null, because it has no left. And when you go on to the right, so which is going to be 6, so you will take that 6. Now again you will explore left and right, both will be null, so that it will just terminate. So this is your pre-order traversal. Is that clear, Maithili, Kalyan? Yeah, so what is the time complexity here? Let's say there are n nodes. So what is the time complexity?
I think it's order of 10.
It's order of n, right? So because you visit every node, na? And what is the space complexity? What is the space complexity, Kalyan?
Structure output, we are taking an element,
Okay,
right?
so for list it is n. Okay, so what else?
Okay.
For stack
Stack
frames?
information, it is n again.
Stack frame, how much it is?
It is n again.
How, when it can be n? So let's say you have a tree called something like this: 1, 2, 3, 4. So let's say,
Q, G.
so let's say not this way. If you have a tree something like this, 1, 2, 3, 4, then it keep on moving on to left, so which is equivalent to, it is equivalent to size of the number
Depth
of
of the
nodes, so
tree.
that the stack frame count also will be n.
Yeah.
Okay, so this is a recursive code. So let me simply write that code. So what I'm saying, so you will just have a DFS, you will pass this root, and you will also pass our result. Okay, so private void dfs of tree node, so you will get a root and list of integers list. So what is our job? So if base case is if root is null, so you don't have to do any operation. Otherwise what you take, just add the current root value, then traverse for left first, then after traverse for right. Done. So finally you will just return list, right? Clear now? What happened? Okay, I need to pass list. Okay, so that's it. Okay, now we have written a DFS code, right? How do you want to, how can you convert this into iterative logic? I want to convert this into iterative logic. So how do you do that?
Use queue data structure.
Can queue will work? How are you what are you doing in pre-order traversal? What are you doing in pre-order traversal?
We are going to the depth of it and then returning.
Yeah, so can queue allow us to move on to depth?
Mm,
I think we can take stack.
yeah.
Yeah, so we can take stack, right? Yeah, how do you want to do that?
Like stack will basically contain here the tree node.
Hmm.
At
So
first
what are
we'll
you
push the
closely,
root and
yeah,
then iteratively we can go.
yeah, so please closely understand. So let's say you have a you have a tree something like this: 1 2 3 4 5 6 7. So what is the in order traversal here? Maithili, can you tell me what is the in order traversal here? Sorry, it is pre-order. So what is the pre-order traversal here?
1, 2, 3, 4, 5.
Yeah, that's it, right? So 1 2 3 4 5 6 7. So what did you understand here?
Sorted.
Ajay, can you tell me what can Ajay or Kalyan? Can you tell me what did you understand here?
We need to, as the start is,
Hmm.
we have to go till end, then add elements when we reach the end.
Till where till where we should do? So we should go to the depth for sure, but how do you go on to the depth? I given very valid test case. You can determine a logic based on this test case.
When both left and right is null,
Hmm. Okay, so let me explain. Simple, buddy. So what are you doing? If you closely see, first we go on to the depth, right? This is my depth, correct? Yes or no, buddy? You are going on to the depth, right? When you are moving on to the depth, on which side you are taking the priority? Left part, right? Yes or no? Yes or no? Once the left is done, then you will move on to the right part, right? When you are moving on to the right part, again you are going on to the left, then you are trying to traversing on to the right. So it is very critical logic. So what, so one thing for sure, the complexity here you involved is, first we move on to the depth. Okay, fine. So when I move on to the depth, so 1 2 3 4, so whenever you are moving on to the depth, so you will always consider left only, because it's a root left and right. So first you will move on to the left depth, and when, so first this is your root. So first you take 1 2 3 4, and there is no left here, there is no left here. Then what you do, what you do, so let's say for your clarity sake, so let me take if I explain the code, it is pretty easy, but I don't want to do that. So let's say you have 10 and 9 here. So definitely pre-order traversal is going to be 10 and 9. So 1 2 3 4 5 6 7, then 10 and 9. So this is how it should be. Now let's say how it works. So the understanding here is if you closely see, this is my current element. Okay, so I take that current element, then what I did, I traverse the complete left, then I traverse the complete left. So if you closely see, this is my complete left for the current element, then I went on to the right, so this is my right part, right? So same is applicable for every node level. So how do you want to solve it? One thing for sure, this is my current, right? So this is my current. when i come here when I come here, there is no left, then I must move on to the right. I must move on to the right, and when there is a right, I need to process that right. Then I will move on to, once I process this right, and I can understand that for this one, complete left part was done. Then I should move on to the right part, right? So there are two things. One is I should know the current pointer, so I should have a current pointer, so which is always talking about where I should start the uh, ordering of the elements. And other is to reach to the depth. If you closely see, this is my current pointer, so this is my current. So to reach to the depth, I should must reach to the depth. While reaching to the depth, there are two things I should take care. So this is my depth. So to reach to the depth, there are two things I should take care. One is whenever I am reaching to the depth, I will always refer to the left pointer only, and whatever left I visit, I will just take that left into result. So let's say how it works. Then after, what I will do when I am going on to the depth, I am also holding this value into the stack, because if you closely see, once I am done with this depth left part, I should handle the right part also. So let's say how it works. So initially I'll have current as 1. Okay, so as long as current not equal to null, I will just hold into the stack. So this is my stack. Okay, so this is my stack. So current not equal to null, I'll take 1. Then I'll move on to the left. So current dot left not equal to null, I'll just keep on adding into the stack. Okay, so 2 is added, then I'll move here. So 3 is also added, then I'll move here. 4 is also added. So one more important thing is, whenever you are adding element to the stack, all these elements were being added to the stack. So whenever you are adding, you are also copy those elements into the list. So in this case, 4 elements I added as of now, so that I copied all those 4 elements into the list. 1 added, copied, 2 added, copied, 3 added, copied, 4 added, copied. It means, what does it mean? You went on to the depth. So you went on to the depth. So there is no depth you would find. It means there is no left. It means indirectly for this node, there is no left found. So that it's time for me to move on to the right. So when I am moving on to the right, so how do I know? There is a right? So what you should do, first take the last element from the stack. So the last element from the stack equal to 4. So that what I will do, I'll pop the last element from the stack, so that current equal last element from the stack. So this is popped. Now you got 4. Now which is already traversed. So the whatever element present in stack which is already been processed, it means it is processed as part of left traversal, because when you are moving on to the depth, you are always looking into the left only. So the left will cover root and left node, so both will be covered. So that you take the top value from the stack, then just make sure that you just say current equal current dot right. That's it. Now current dot right means this is my current, so current dot right equal to 5. So what does it mean? Earlier current is starting from root, and you keep on adding all the values. You just move on to the depth. It means you keep on, you just move on to the left. So it means you are covering the root and left traversal. So it means pre-order will have root and left. So you are done with root and left traversal. Then once you are done with root and left, then take the top element, move on to the right. Okay, so now current equal to 5, right? So now what is your job? Again, you need to apply the same concept. So first you add 5 to the stack, 5 to the list. then 5 has a left also, 6 to the stack, 6 to the list. Done. So it means you are done. Now there is no left here, so again you need to traverse right for 6. So the current is going to be what? Hope you are following me. So you just so once what we did, if you closely see, this is what we did, right? So we started from root and we went on to the left. 4 elements were there and there is no left. You pop the 4 and you move on to the right. So right is going to be 5. So current is 5 now. So you just added 5 to the stack and 5 is added to the list, and 5 has left 6 to the stack, 6 has been added to the list, and there is no left, so that it's time for me to stop. Now what I will do, now I need to replace the current, right? So current, when current is here, so current dot left means current is here, so current is null. So when current is null, now it means there is no left to this node, so that it's time for me to go on to the right. So current equal current dot right, so current equal current dot right, so current dot right also null. So it means you popped it, you went on to the you popped it from the stack, and current equal to 6 right, so 6 right also null, so that it's time for me to look on to the next element from the stack. So the next element from the stack is 5, so you take 5, so stack dot pop equal to 5. Now you got 5. Now 5 left, so 5 left is already been processed earlier, so now you get on to 5 right, so that 5 right current is going to be current dot right, so it is means current dot right is 7. So 7 is there, so now it's time for me to process this 7. So 7 again will be added to the stack, 7 is also added to the list. Done. Now there is no left, there is no right, so that ultimately this will also done. So when you pop it, so this doesn't have left, doesn't have right, so that this will also be done. Now next element is 3. Now again you pop 3 from the stack. This the 3 left is already done, so while processing 3 only you went on to the left, so when you try to move on to the right, there is no right, so that 3 also done. Now again when you pop from the stack, you will get 2 right, there is no right for the 2, so that 2 also done. Then what is your job? Next you pop 1, so means current equal to 1 now. So 1 left is already done, so that it's time for me to apply current equal to pop element dot right, so right is going to be 10. Now it's time for me to add 10 and its left, so 10 is been added here, and its left is 9, so 9 also been added here. So it means whenever you are adding to the stack, you are adding to the result also. Now when you pop 9, you try to look into 9 right, so there is no right for the 9, so that this is done. Then next element of next you pop 10, so when you look for 10 right, so there is no right for 10, so that you are done with this also. So these are the, of course you just add here, so these are the elements we have done as part of iterative process. Is it clear, buddy? Ajay, Maithili, Kalyan. Maithili, is it confusing? Perfect. So now how do you come up, what is the time complexity here, please? What is the time complexity?
Order of n.
Okay, order of n. So what is the space complexity? For the stack, so how much space it will take? So for list it is order of n. And for stack, how much it is? Order of n only, na? Because if you have all screw trees, so the stack will contain all the elements. Okay, right? So how do you write a logic here? There are 2 pointers I need to consider, right? So one is current, another one is a stack, right? So how do you write a logic here? So one is tree node, current, which is root, so which is starting from root. Another one is stack, right? So stack of tree nodes, so which is stack, new stack, right? So how do you want to go with it? So there are 2 cases, right? So 2 things I need to consider, and you will have this list. Okay, so you will have this list, right? So now let's say how do you want to solve it? So what is the condition I should do here? Can you please tell me what is the condition I should do?
Root dot left not equal to null.
That we can do. first of all, our current should not be null, right? So we holded root into current, right?
Yes.
Yeah. You can handle with that root also, but I just take the current. Okay. So what else I should do?
Until unless your stack is not empty.
Is it end condition or or condition I should do? Okay. So as long as stack is not empty, is it end or I should keep in the middle?
Mm,
At the top level itself, we can return if the root is
Yeah.
null, right?
That's
Root
okay.
itself is null, no need to add into
That
the
we
stack.
can handle here also. Yeah, yeah. That's a base case. It's not required, but it's fine. Yeah, so in the while condition, I did current not equal to null and stack is not empty, right? Do I need to put end or or? Is it end or or?
I mean, current should always be there.
Why
So
it
there
always be
is
there? It can be null also, right? If you closely see, here current becomes null, right?
mm,
Here current becomes null, right?
we are adding null count. Okay.
The current not equal to null or stack is not empty.
Or, right? So it should be or because so when the current is null, you pick the element from the stack and move on to the right. Okay. So what is your job? First, we should move on to the depth. Correct, please. I should move on to the depth, right? So how do I move on to the depth? Please. Left depth I should move on now, please. So is it clear? So I just went on to the left, right? Correct? Is this correct? If the current
Yes.
is not equal
Yeah,
to
for
null,
the
I
depth
should
we need
move
to
on to
do
the
it.
depth, right? So this is what we did, right? So first what we did, uh, so we just started from root. I will just move on to the depth, right? So 1, 2, 3, 4, it is all or left only. So when it becomes current null, then we should move on to the, we should take the top value from the stack and move on to the right. Yes, that's a simple logic. So what we did, every time whenever you move on to the, so whenever you move on to the left, it's time for us to add that result to the list. So list dot add dot current dot values. That's what we did. So then what we did, now it's time for me to tree dot node. It's time for me to take the top value from the stack so that previous previous node you can say. So you can take it from stack and now current equal to previous node dot right. Correct now, buddy? Correct? Maitri, is that correct?
Yeah.
Done na? Do we have we covered everything or do we need to do anything else?
We need to add elements to the stack.
Yeah, thanks. So I
Yeah.
forgot to add to stack. So stack dot. So first you will add to the list at the same time stack dot push off current. Okay, so just add the current, then move on to the left. So let's run. That's it. So it is very critical logic. So you have to be. What is that? Yeah, it went good. Okay. So it is little critical logic, but you need to be very careful about how do you traverse on the tree. Is this clear, buddy? Ajay? Maithili, are you clear? Yeah. Yeah, so you can also spend little bit time so that this will be simple. So the only confusion you generally tend to get is how come right values gets to be added. So first if you closely see, this is what we did, right? So we traverse left, so we started from root and we traverse complete left. Then we take the top value and we try to reassign current equal current dot right so that this will be done. So 5 6 will be done, then this. So that's how it went. Okay, so this is how the pre-order works. So you can also come up with different data structure to write a pre-order traversal, but this is one of the way. but whatever data structure you use, you must and should use the concept of stack. Okay, so let's solve a couple of problems here. Okay, so this is done. So now let's see how do you solve n array pre-order traversal. Okay, so this is n array pre-order traversal. So how do you want to solve it? So right now, earlier we have what? Earlier we have uh, only left node and right node, right? But in this case, it is having the root node will have list of childrens. Okay, so this is called n array tree. So earlier we looked for binary tree. Now it is going to be n array tree. This is not a complex thing to understand. So let's see how do you solve for pre-order traversal for n array tree. So let's say you have 1, then 3, 2, 4, then what is your job? So here you have 5 and 6, right? So earlier you have only left and right. So first you traverse left, you move on to the right, right? But in the now you will also have middle nodes also. So how do you want to traverse now? So this is how it should be, right? So first you traverse this one, then you went on to this, then you went on to this, you are done with left, then you are moving on to the next element. So this is going to be E4. Now it means you are done with complete left part, then you move on to the next element. So this is going to be E5, this is going to be E6. So total the order could be 1, 3, 5, 6, 2, 4. Correct na? Correct na, buddy? Ajay, Maithili, is that clear? Yeah. Now how do you want to solve it? Can you try this? I think it's not a complex problem. So here it's only earlier you have left and right, but now it is going to be list of nodes. It's a very good problem to practice, so please give a try. So definitely you can able to solve it. I just spend some time, solve with both recursive and iterative approach. Okay, let's move on to next problem. Yeah. Okay, so we need to invert the binary tree. So what does it mean inversion, right? So you just need to change left node to the right, right node to the left. That's it. So it should be applied recursively. So that is how it should be. So let's say he has given very good example. So let me walk through that. Let's say you have element 4, 2, 7 and 1, 3, then 6, 9, right? So we need to invert the binary tree. So what we should do, so let's say this is my root. Okay, so my root is 4. Invert means you just need to change the references. Left should be moved to right, right should be moved to left. So it means for this 4, this is left and this is right. So those two should be exchanged. Left should come to right, right should come to left. Okay, so that's how it is. Now again, if you closely see, for this 7, this is right and this is left, right? So both should be changed. So 9, 6, and this is also left, this is right, right? So this will also change. 3, 1. So we just need to invert. Okay, so that's how it should be. Is the problem statement clear? Ajay, Kalyan, Maithili. Okay, how do you want to do it?
Shinu will begin with the root.
Hmm.
We'll take a temp variable where the left will store temporarily, then swap it.
Yeah, swap it. Then what you do?
Then iteratively we'll pass the left and the right again.
Yeah. So first of all, how you should do is all the tree problems, right? Don't apply any brain. Okay, if you apply brain, you will definitely get confused. So blindly think about recursive logic, then just do that. That's it. It will take care of everything. So what we do, if you go with the recursive logic, so how it will work? So first I will call DFS of 4. Okay, now it will have left and right. So what I will do, first I will keep I'll keep temp, so I'll keep right to the temp or left to the temp. So let's say I will keep right is 7, right is present in temp. Now what I do, root dot right I will make it as temp, sorry, root dot right equal to root dot left, so it means right will come here. Then root dot left equal temp, so temp you already copied, right? Now it's time for us to apply the same logic for these two. So DFS of, now it's time for to apply DFS of 7, DFS of 2. Now again same logic. So for 7 you have right, so right you keep it temp, then root dot right equal left, so left is having 6, then right is having 9, so temp you will just append temp, so temp will become, now again this called DFS of this one, DFS of this one, so left and right both are null, so that you don't need to do it. Similarly for 2, so when you go on to 2, again same thing, so you have right you can keep in temp, root dot right equal left, you will just apply left, and left is going to be the temp. Done. Is that clear, buddy? Is that clear, Ajay, Kalyan? So what is the time complexity here? What is the time complexity here?
Order of n.
Yeah, so it definitely order of n, right? So because when it is screw tree, you just move on to the depth. And what is the space complexity?
I'm going with DFS recursion, it will be n.
Again order of n, right? Because if you have a screw tree, you just move on to the depth, keep on. Simple, na? So let's, I will write a recursive code. Iterative code, how do you want to do it? It's up to you. So it's up to you. How do you want to go with iterative approach? As we know a lot of things, right? So you can use any technique. Okay, so let's say, so this is my if root is null, you will just return root. There is no change. Otherwise, what is your job? So tree node temp equal root dot right and root dot right equal to root dot left. So root dot left, which is equal temp. Then finally you will call invert t for, yeah, whichever you want to go. So root dot left, invert t for root dot right. Done. So finally you will just return root. Done, buddy. Done. Is it clear or any confusion? Kalyan? Okay, so that's it, buddy. So if you want, but if you want to do with yeah, can you tell me, one is pre-order travel, you can use, if I want to solve this with iterative approach, one is pre-order traversal. uh, what else I can use? Can you solve it, can you solve this with iterative approach, Ajay, Kalyan? If I want to solve this
Yeah.
through iterative approach, how do you want to do it?
Can you take the same concept of stack and do it?
Yes. Do you, if you closely see, this is not a pre-order traversal. Am I not doing pre-order traversal? Yes or no?
Yeah.
Earlier I just
Going to
did
left, right.
root dot value, then now I did pre-order traversal, right? Okay, it's a concept of stack. So it's all about how do you want to solve this. Okay, so if I want to solve with stack, then how do you want to solve with stack, or do you find any other simplest solution? Okay, if you go with stack, then how do you want to solve this through stack?
Actually, Shreya, if you go with stack, then the way when you retrieve it, it comes in reverse order.
That's what
But
I'm.
if you go with the queue,
No, no.
then we can take
I
the left.
understand that. I understand that. I
Yeah.
understand your point. But if I really want to do with stack, how does it really work or not? You know how it works
Uh,
is earlier what we did. What is the stack implementation earlier? It's a purely recursive logic of. It's a purely recursion code in the form of iterative approach, right?
correct.
Okay, Maithili. Why it is getting stuck? Okay, so earlier, whatever we did, it's a purely recursive logic, right? So if you closely see, earlier also we have solved. Where is it? This one, right? So earlier also we have solved. In this place, what we did, we just added root dot value to the list. Then you just went on to root dot left and root dot right, right? What is the problem if I use stack there? Does stack works or not? Can you tell me for the same logic? If I want to go with stack, how should I go?
So, first we'll begin with root node 4. We'll put that to stack. Okay. Then we will check whether stack is empty or not. Obviously, stack is not empty. We'll take out 4. Then we'll take 2 and 7 and we will swap it and put it to the stack again. And we'll keep on repeating that until the stack is,
No,
as
you
long as
should
stack
take
is
care
not
about
empty.
all the subnodes also, right? When it comes to subnode and when you, yeah, yeah. I got your thought. I got your thought. Perfect. So that is one best way. Yeah, actually you are using concept of level order, but you are applying stack. So, but if I want to solve this through pre-order concept, how should I do it? So you are saying is first I add to the 4 is there.
Yeah.
4 is there. So 4 has left and right, right? 4 has left and right. Then what I do? For this 4 I will just swap left and right. Then I'll add 7 and 2 to the stack, right?
Yeah, we'll push the left one to the stack, then the right
Then
one to
when you
the
get
stack.
7, yeah, yeah, others got it. One idea is doesn't matter, right? We just need to swap. We just need to swap and we just need to know. So if I want to swap, I need to know the parent, right? So first of all, I am starting with parent 4. Okay, so what I'll do, I'll take left. So left is 2 and right is 7. Okay, I will just swap them. So I will just swap them. So I'll just add root dot left equal right, root dot right equal left. So I just did that. Then I will add these two elements to the stack. So in whichever order you do, that doesn't matter. So I'll just add 2 and 7 to the stack. So once I add 2 and 7 to the stack, next iteration I'll take 7 because I just take the stack dot pop, so I'll get the 7. So 7 left and right was there, right? Again I will just swap 9 and 6. I will add 9 and 6 to the stack. Now when I pop 6, there is no left and right for 6, so done. When I next I pop 7, 9, there is no left and right for 9, so that is also done. Now when I pop 2, now I get 2. So when I pop next element, which is 2, so I got 2, so 2 has left and right, so that I will swap. Then again I will add 1 and 3 to the stack. Now when I pop 3, so there are no left and right. Then when I pop 1, there are no left and right, so you are done with construction of tree. Is that clear, buddy, what I said? Maithili, are you clear? Yeah, so okay, so this is a because here we don't need to worry about order of elements, right? So we don't need to worry about order of elements. It's all about changing the references, right? So that's what we are trying to do. So this is what we are trying to do. If you closely see, so first uh, simple. So let's say if root is null, you will simply return root. Otherwise, what is your job? So it's time for us to stack dot tree node. This is my stack and new stack, and stack dot push of root. So as long as my stack is not empty, I should follow this process. So what I do, I will take the tree node current, which is going to be stack dot pop. Correct. So this is my current, so which is stack dot pop. Simple, same thing. So current dot. So just do the temp tree node. Temp equal to current dot left. Then just say current dot left equal to current dot right, and current dot right, which is equal to temp. That's it. So then what is our job? So it's time for us to push these two elements. So stack dot push off current dot left, and stack dot push off current dot right. So what is the mistake we are doing? Can you tell me? What is the mistake we are doing here? And finally we will
We
just
need to
return.
put a null check, right?
Yeah, so we just
See
need
what
to
is
put null check. Okay, so when do you do that? When do you want to do that?
before we push to the stack.
Yeah, simple. So if current not equal to null, you just current dot left.
Why not before swapping?
Before swapping, does it need it? Okay, so you want to say you can do that, but it doesn't seems to be clean code, because if you handle here, it will automatically handle here, right? Let's say both are null. When both are null, when the current one, let's say you have only leaf node and left is null, right is null, so the left and right again set to null, and here it will be trigger, it will here it will be handled. Again you end up adding to the stack, right? So when you end up adding to the stack, that time again you have to do the check. But if you do there
So no, I
again,
think with that condition, it will not push into the stack if it is null, right?
yeah,
In the first place itself. Yeah.
yeah,
At line
so
31, we have a condition.
yeah,
Yeah,
it
if it is
will not
null,
push. Even if you apply here again, you should apply same condition should be applied here, because
yeah.
that's where you can handle one. And can I use a queue here? Can I use queue here? Why are you worrying, buddy? All
Yeah,
about
same. Same.
same thing, right? Doesn't matter, na?
Yes.
Doesn't matter, right? It's only reference of variables, na? So queue doesn't have push method. Does it matter on which order you are trying to do it? Doesn't matter, right? Both will be same, na? Where I'm just adding reference name making same, so it doesn't matter in which order you order, it doesn't matter. It does the same operation, right? So reference of variables is more important. I think you can solve this problem. So same tree, right? Yeah, so can you tell me, so you will be given a tree, and there are two trees, okay? We need to say both the trees are same or not. So means root values and its children values should be same. See 1 1, here left is 2, here also left is 2, here right is 3, right is also 3. So this is not same, right? So 1 dot left is 2, but for this tree left is not having value, so that here you should return false. And even in this case also 1 correct, but 1 left is 2, but this one left is 1, so this is also not valid, so we need to return false. Is the problem statement clear?
Yes.
Maithili, are you clear? Okay, how do you want to solve it, man? What I said, don't think about iterative logic first. So if you want to solve these problems, all the tree problems, graph problems, and whatever topics we are going to learn from now onwards, right? Everything you must be very clear about recursive code. Done. So once you, so how do you want to solve it? I have 1 2 3 and one more tree. 1 2 3.
Just traverse and then
This is
you know
root 1
go
and this is root 2.
yeah
Okay. Yeah.
pre-order it and compare. If it's not same, return.
Okay, tell me base case for returning false. Tell me base case.
Root 1 dot value,
Root
if
one,
not
yeah.
equal to root 2 value, return
Mm.
return false.
Okay, let's say you have this one. And what is the base case here? Here it is false now, yes or no?
Yeah.
Mm.
So how do you cover the base case? Base case is only the use case. Base case is only the tricky part here. All others. First of all, what is my recursive method? Let's say it is a DFS. What? How many parameters it takes?
Root 1 and root 2.
Can this be handled with 2 parameters?
I think yes, because anyways in recursive we'll be going to left and right, right?
That's good. So it can be handled with 2 parameters. Now what is the base case you should write?
Initially, those should not, I mean,
Those should not be null
be
and
null.
both should not be equal.
Equal.
Okay,
Sorry,
both should not be.
yeah, should not be equal, correct.
Yeah. So one is if root 1, okay, not equal to null, and root 2 not equal to null. So let me, okay. So R1 comma R2 both are not equal to null, and R1 value not equal to R2 value, then you return false, right? Yes or no?
Yes.
And okay, so what is other case? Okay, this is perfect. So what is the other case? Think, man. If you compare this test case, you will get other case. Once you one, for example, this test case is passed. Okay, let's say, can you tell me this test case is failed? Okay, so it means this is not the case. It didn't come into this case. When it will not go into this inside?
1 to 3, 1 to 3 case.
Sorry.
I mean,
No,
first,
you said R1 and R2 both not equal to null, and values also V1 V2 values also not equal to null, you will return false, right? When this condition will be true? Okay, so let's say if you want to solve this for this problem, how do you want to solve it? So 1 2 and 1 2, right? Yeah, so what will happen? First you will pass 1 1, right? Correct na? Both are equal. Then what you pass? 1 left, 1 left, then this one left, which is null, right? Correct na? Then you will pass this right. So this one right is null, and this right is 2, right? And you will apply end condition for this. So you will call DFS of for this case. So this is left and left, this is right and right. This is R1 left, this is R2 left, this is R1 right, this is R2 right. Right? Do I need to return false or true here?
In this case, false.
Yeah, how do you handle that?
Root 1 dot left not equal to null. It can be null, right?
You can do that, but
Either of them being null.
yeah, that's it na. Either of being null, return false na. First you will have this check. If this check is failed, if any one of them is null, then again return true, return false na. Correct na, buddy?
Yeah.
Correct. Yeah.
Otherwise you can move on to the next case. Yeah, that's a good catch. So I think you can come up with the iterative approach for this. So what is our job? If P not equal to null and Q not equal to null and P dot value not equal to Q dot value, then you will just return false. Okay. Otherwise, what is your job? If P is null or Q is null, then return false. Okay. uh, when both are null, right? So then yeah, so both are null, you can return true because that is valid. If one of them is null, you can return false. Correct na? Please. Yes or nobody? Both are null, you can return true. If one of them is null, you can return false. Okay, then what is our job now? It's time for us to it means both are equal, so it means both are equal. So now actually this being the leaf node, so this is first test case, this is second, and this is last. And what is our job? So you have to apply the same concept for left and right, right? So what is your job? So return is same p1 dot left and so p dot left and q dot left, and you should also compare right also. Okay, so is same p dot right and q dot right. Clear, buddy? What is the time complexity? What's the time complexity, buddy?
Same, right? Order of n.
Order of n, right? So the space complexity also remains same, right? Okay, can you tell me how do you handle this through iterative approach? What is the data structure you go with it to write a clean code? Maithili will answer that.
What's the
I think you are traveling. Okay. So Kalyan Ajay, can you tell me what is the data structure is the better one? I couldn't hear you, Maithili, but fine.
I think Q would be.
Yeah, Q.
Yeah,
Because we
Q
have
is
left
the
and
best.
right, right? So
Yeah,
we
so
can
Q
put
is the
and
best data
pull
structure,
again.
right? So that you can apply because it's a level order, right? If you closely see, this is a concept of level order, right? So let's say you have data something like this: 1, 2, 3, 4, 5, 6, 7, right? Then again you have 1, 2, 3, 4, 5, 6, 7, right? So how do you compare now? In the queue first you will have, so please closely understand, in the queue first you will have 1 comma 1, correct? Correct now, buddy? Please, buddy.
Yes.
This one and this one, right? In the next level what you will have, please?
2, 3.
No, if you go with that, gone. What you will have next level?
2, 2 and 3, 3.
That's it, right? So 2, 2, then 3, 3, correct? First you will add this left and this left, then this left and this left, right? Each time you will pop 2 elements, then compare. In the next level, how it will look like? In the next level, how it will be, please? This 4 and this 4, right? Because you get this 2 and this 2, right? For this 2 you will get 4, this 4, and for this 2 you will get this 4, and for this 2 you will have 5, for this 2 also you will have 5. Then we are done with these two. Then when you pop these two, then you will try to compare this left and this left. So you will add this left and this left, and this right and this right. 7, 7, correct? So now you pop these two elements, these are valid. Then you, because it doesn't have left and right, so no worries. You pop these two elements, these are equal. You pop these two elements, these are equal. You pop these two elements, these are equal. It doesn't add any elements because all are leaf nodes, right? So now if you have something like this, what will happen? So 1 2 and 1 2. So what will happen? So first you will have 1 comma 1 in the queue, right? Now done. So now what, you pop these two. So first you will have left, one left is 2, this one left is null, then this one right is null, then this one right is 2. Now when you pop these elements, you understand that one of them is null, so you will just return false. Clear, huh? Ajay, Kalyan, these problems seems to be very simple after solving DQ problems. Can you write our okay, so let me quickly do that. So simply, what is your job? Renode queue and new linked list. Try to come up with multiple solutions. Okay, so if you go with stack, it will not work, buddy, because you need to compare the elements in the order. That's where you should go with the queue. Okay, so what is your job? So queue dot add of p and q dot add of q. But earlier problem doesn't need order, so that you can simply go with the stack, but in this case you need order. Okay, so what is our job? So tree node root 1, I can say r1, so q dot pool tree node r2, which is also q dot pool. Okay, now what you do, if both are null, no worries. So r1 is null and r2 is null, then you will just continue. So that's fine. If any one of them is null, I think this is the best way to write. I think if any one of them is null, or both the values not equal, then you can return false. Correct, nobody? Please. Correct, na? Then what is the next job now? What is the next job now? Q dot add of
q dot r1 dot left.
Then r1 dot right. No, man.
R1 R2 dot
R2 dot left.
So basically, first push all the left ones, then go to the
right. That's
right.
that's where you will compare, right? Because when you pop it, it will have the same order. So lefts you will compare those lefts, and that's how it works. So here you don't need to apply level logic. If everything is smooth, then you will just return true. Right? So if something is wrong, here only you can return false. Everything is true, good, you can return true. Now you understand the importance of stack and queue, na? So which is very, very critical. So we need to know how to apply on the data structures. I think you can solve the fifth problem. I think you can easily solve fifth problem, so that tomorrow we can discuss about remaining problems. See how quickly we are moving on. Today we discussed 5 problems. With this knowledge, you can easily solve a symmetric tree. So what do you mean by symmetric tree? So symmetric means mirror, right? So when you look at on mirror, left will shown as a right, right will shown as a left, right? So if you see, is it symmetric or not? So it means if I reverse this tree, if I you understood, right? So when you look at on mirror, so it means this left child left value should be equal to right child right value. Yeah, so we need to see, is it symmetric or not. So it means when you look at the mirror, right, so it will be left will come as a right, right will come as a left, right? So it means when you show on the right part on the mirror, can it look as a left part? So that's what he's trying to say. In this case, very simple. So this is my root, left is 2, left value is equivalent to right. Perfect. So when I come here, this left value is equivalent to other child right value or not. So here left 2 left is 3, other child 2 right is 3. So this is fine. And this 2 right is 4, other child 2 left is 4. So this is also same. So that we can call it as a symmetric. But when it comes to here, this left and right is clear. Now when it comes to this left should be equal to this right, but this is not having left, but this is having right, so that you should return false. It is same tree, but it is not mirror tree, right? Understood,
Yes,
Ajay?
there is symmetry. Yeah.
So Ajay, Maithili, is it clear, or do you want me to walk through the diagram? Maithili, understood?
So anyway, we will reflect the like just revert it and then check if both are identical. It's
Yeah.
a combination of last two problems.
In the last problem, this will return
Okay.
true, right? But in this problem, this will return false. In the last problem, we just seen that both the trees are same or not, but in this case, both the trees should be in reverse order, so that when you mirror it, you will get the other part, right? How do you want to solve it? Is the problem statement clear, Maithili?
Yeah.
Yeah, how do you solve it, Ajay, Kalyan, Maithili? Any logic? So what I said, you want to go with the recursive logic, right? So how do you want to go with recursive logic? I will just give the algorithm so that you can give a try, so that it will be good practice for you. Let me take this input. Okay.
It should be the left value equals to the right value.
That's it, right? So it is same
Yeah.
as previous problem, but what is our thing? We just need to. It's a simple code change, right? Yes or no, Ajay?
Yes. Like instead of compare left to left, he will compare left to right,
That's it.
right to left.
Done,
That's
done,
it.
done, done. So you are able to solve it. I think we don't need to discuss on it. So you can also give a try. Uh, okay, so done. Let's stop today here. Tomorrow we will try to pick up other problems. Uh, the goal, my goal is I want to do all four patterns in parallel. Let's do one thing. What we do first, we solve pre-order. I think couple of problems. I think we solved 5 today, right? Uh, then we'll also solve in order top 10 problems, post order, level order. Then we will try to pick up the problems randomly and we see the differences. That way you will get a little clarity. Let's see how it goes. Okay. Yeah. Thanks for your time. See you tomorrow. Do you have any questions? Yeah, if no questions, good. Yeah, if possible, try to solve below problems too. I think with this knowledge, you can solve below problems. I think this one you can solve path sum. The next problems needs a little observation on recursion, but you can still do that. If you are unable to do it, we can discuss tomorrow. Okay, but you must practice these 5 problems. Though it is simple problems, if you practice, it will really help us for advanced level and intermediate level. So actually, I was aimed to complete these 10 problems in this session only, but initially 2 problems took a lot of time. Otherwise, these 10 could have done this session only. Yeah, after solving DQ problems now, these are nothing. Though actually we have seen very hardest problems. Even the graph problems also you feel the same. Okay, let me stop recording.